unidirectional transport in Cartesian, cylindrical and spherical coordinate systems. In this lecture, we will start looking at pressure driven flows. So far in our discussion, we have defined the shear stress tau x z say as mu times dVx by dz for a flow in which the velocity is in the x direction and the velocity gradient is in the z direction. Okay. So, for example, for a flow of this kind where this is x and this is z. Okay. This is the rate of transport of x momentum in the z direction or the flux of x momentum in the z direction per unit the flux of x momentum in the z direction or the rate of transport of x momentum in the z direction per unit area or the force exerted per unit area at a surface. The force exerted in the x direction, the force exerted in the x direction at a surface, the force exerted in the x direction at a surface whose outward perpendicular is in the z direction. Okay. So, the outward perpendicular, the unit normal is in the z direction. Okay. And this takes place due to momentum diffusion. Okay. So, this we have seen so far. There is another mechanism of transport and that is due to pressure. There is no equivalent of pressure for heat and mass transport, because in the case of heat and mass transport, the quantities being transported, energy and mass, are scalars and the flux is a vector which has direction, the direction of transport or the direction perpendicular to the surface. In the case of momentum, there are two directions associated. One is the direction of the force or the direction of momentum, which is a vector, and the second is the direction of transport, the direction in which momentum is being transported. So, shear stress is due to velocity variations, due to variations in the velocity. You can have a second mechanism of transport called the pressure, which is actually non-zero even if there is no velocity. Okay. So, for example, if you had a fluid in a gravitational field, there is a non-zero pressure. There is a non-zero pressure at a point within the fluid, even with if the fluid is at rest, because of the hydrostatic head above this this location. Because of that, you will have a force exerted even when the fluid is at rest. That force exerted is always perpendicular to the surface. The force exerted by pressure is always perpendicular to the surface. It is perpendicular to the surface at all locations. So, the direction of the pressure is always along the perpendicular to the surface, the inward perpendicular to the surface. If you had a fluid volume element, if you had a surface within a fluid, if the perpendicular to the surface is in the x direction, z direction say, the pressure will act in the minus z direction at the surface. The pressure for a surface whose outward unit perpendicular is in the plus z direction, the pressure will act in the minus z direction. At that same location, if you had a surface whose outward perpendicular was in the y direction, the pressure would act in the minus y direction at the same location. So, depending upon the orientation of the surface, the direction of the pressure changes. Pressure is always perpendicular to the surface and it is always compressive, that is, it is directed perpendicular to the surface along the inward unit normal to the surface. So, the pressure at a differential volume, the pressure for a differential volume is always directed along the inward perpendicular to the surface. It is compressive and therefore, it is always directed along the inward perpendicular to the surface. And the force per unit area on the surface is equal to the pressure. Pressure times the surface area will give you the force that is exerted on the surface that tends to compress the volume element. So, that briefly is a description of pressure. It is important to make a distinction between thermodynamic and dynamical pressure. Okay. The thermodynamic pressure is the pressure, for example, that you get from the ideal gas equation of state. Okay. P is equal to N kBT, for example, okay, where N is the number of molecules per unit volume. Kb times T is an energy. Okay. Kb times T is an energy. Kb is energy per unit temperature increment, and therefore, Kb times T is an energy. N is number of molecules per unit volume. So, N kBT is energy by volume, which is the same as force divided by area. Okay. So, this is the thermodynamic pressure. Okay. It is the equilibrium pressure. Okay. It decreases to 0 when the number density goes to 0 or when the absolute temperature goes to 0. Note that here T is the absolute temperature measured in kelvins. So, this is a thermodynamic pressure. There is a 0 reference for that. Okay. The 0 reference is 0 temperature or 0 number density when there is vacuum. Okay. The dynamical pressure, on the other hand, is the pressure within a fluid, whether it is stationary or flowing. Thermodynamic pressure is defined when the system is at equilibrium. Dynamical pressure could be when it is stationary or when it is flowing. Okay. Fluid flow is driven by pressure differences or pressure gradients. Okay. For example, we had looked at the flow in a pipe. Okay. Okay. We had looked at the flow in a pipe. That flow in a pipe is driven by a pressure difference between the two ends. Okay. It is driven by a pressure difference between the two ends of the pipe. Okay. Therefore, here it is the pressure difference that matters. Okay. The absolute pressure does not matter, it is the pressure difference that matters. For the dynamical pressure, in order to compute the fluid velocity, if I add a constant pressure everywhere in the field, the velocity will not change, because the difference in pressure between 2 points has not changed when I have added a constant pressure everywhere. Okay. So, therefore, for incompressible flows where the density is a constant, the velocity is driven only by differences in pressure or gradients in pressure. Okay. The absolute value of the pressure does not matter. Okay. That is why, for example, when we look at pressure driven flow in a pipe, there is also an atmospheric pressure at the two ends. Okay. And therefore, that atmospheric pressure cancels out and does not appear in the pressure difference. Okay. So, if you apply the same pressure difference across two ends of a pipe, whether it is at atmospheric pressure or whether it is at vacuum, the flow rate will still be the same, because the pressure difference is the same. Okay. Therefore, the velocity field depends only upon variations in pressure. Okay. And therefore, you can add or subtract a constant to the total pressure without changing the velocity fields. Okay. Whereas, in thermodynamic pressure you cannot do that, okay, because it is an absolute pressure. So, that is the distinction between dynamical pressures, which are defined only up to an additive constant, okay, because so long as the difference in pressure between different locations in the fluid remains the same, regardless of what the absolute pressure is, the flow rate will remain the same, the velocity field will remain the same. That cannot be done for thermodynamic pressure, because thermodynamic pressure does have an absolute value. Okay. So, in this course we will only be looking at pressure differences, okay, not at absolute values of the pressure itself. Okay. It is the pressure difference that drives the flow. Now, the next thing is the potential flow. Okay. The potential flow is a limiting case of a pressure driven flow where the viscous effects are neglected. Okay. So, basically a potential flow is an inviscid, okay, zero viscosity. and it is incompressible. Okay. Incompressible means a constant density. And there is another condition for potential flow which I will not be able to explain here, we will see it later. It is also what is called irrotational. It is also what is called an irrotational flow. The inviscid approximation, zero viscosity approximation, applies only to high Reynolds number flows, because it is at high Reynolds number that the inertial effects are much larger than viscous effects, and therefore, you can neglect viscosity in the conservation equation. Okay. So, it is only at high Reynolds number that this potential flow approximation is valid. High Reynolds number, but also viscosity is not important, implies that there is no turbulence, because momentum transport due to viscosity is present for turbulent flows as well. Okay. So, that translates into this condition here, what I call irrotational, okay, and I will explain that later when we come to it. Incompressible is of course that the density is a constant. Okay. And for these inviscid irrotational flows, okay, we have the pressure, the relationship between the pressure and the velocity is governed by the Bernoulli equation. Okay. So, the Bernoulli equation is basically P plus half rho V square plus rho G Z is equal to P naught. Okay. P is the pressure, rho is the density, okay, and G is gravitational acceleration. V is the velocity, okay, and Z is equal to the height. Okay. Height in the direction opposite to gravity. Height in the direction opposite to gravity. Okay. Okay. So, if the gravitational acceleration is in this direction, the Z coordinate has to be in this direction, okay, in the direction opposite to gravity. So, this Bernoulli equation defines the pressure in terms of the velocity and the height. On the right side, this P naught is a constant. Okay, on the right side, P naught is a constant. So, this is the Bernoulli equation that can be used to relate the pressure to the velocity. Okay. So, and this is, as you can see, it is an algebraic equation. Okay. One important characteristic of potential flow we have considered to be inviscid, zero viscosity. Okay. That means that the shear stress is equal to 0. Okay. That means that the shear stress is equal to 0. Okay. That means that if I have a fluid flowing close to the boundary, there is no momentum transport perpendicular to the surface, okay, because the shear stress gives you the rate of change of transport of momentum in the x direction perpendicular to a surface whose unit normal is in the z direction. Okay. So, at this surface, for example, if I had a potential flow, there would be no stress exerted, and this stress that is exerted is required to basically, if you have a no slip condition, it is because of the transport of stress that the fluid decelerates and decreases in velocity to 0 at the surface to satisfy the no slip condition, the 0 tangential velocity condition at the surface. Therefore, in an inviscid potential flow, the 0 tangential velocity condition cannot be satisfied. Okay. You can only satisfy the 0 normal velocity condition, that the velocity perpendicular to the surface is equal to 0. Okay. Because we have neglected viscosity, we have basically neglected the diffusive transport of momentum. Okay. and therefore, there can be no momentum transport perpendicular to a surface in order to reduce the velocity to 0 at the surface as required by the no slip condition. So, we cannot apply the tangential velocity boundary conditions at a potential flow. Okay. So, let us look at some applications of how we would use the Bernoulli equation in order to calculate in order to solve problems of potential flow. First thing I will look at is the discharge of a tank. Okay. So, I have a tank here. With an outlet, okay. And initially this tank is filled, the total height is 2 meters, okay, and the height of the discharge is 0.5 meters. Okay. So, the height above the tank is going to be 1.5 meters. Okay. The height of the fluid above the discharge is going to be 1.5 meters. Okay. And area of tank is 2 meters square. Okay. The diameter of outlet is 2 centimeters. Okay. And let us assume that this is filled with water of density 10 power 3 kg per meter cubed. Okay. Water with density 10 power 3 kg per meter cubed. Okay. Now, what I want to find out is how long does it take for the discharge of the tank, that is for the water level to decrease to the same level as the outlet. Okay. And as the water is being discharged, okay, what is the maximum distance that would be travelled, okay, due to this discharge into the atmosphere. Okay. So, those are two things that I want to find out. Okay. So, as the tank discharges, there is going to be a decrease in the height of the surface, okay. And this velocity of the surface is going to be related to the velocity at the outlet, okay, which I will call VO. I will assume that the outlet velocity is horizontal. The velocity decrease in the height of the surface, okay, the rate of decrease of the height of the surface is going to be related to the velocity at the outlet, okay, by the condition that the flow rates have to be the same. Okay. The total volume that has decreased on top has to be equal to the total volume that has left the fluid. Okay. The decrease in volume at the top is going to be equal to the area of the tank times the surface velocity. Okay. This has to be equal to the area of the outlet times the velocity of the outlet. Okay. And this implies that the velocity of the outlet is equal to the area of the tank times the velocity of the surface divided by the area of the outlet. Okay. That is the relation between the velocity of the tank and the velocity of the surface downwards and the velocity of the fluid from the outlet. Of course, if the tank area is much larger than the area of the outlet, then the velocity of the surface is very small and it can be neglected. Okay. And we will see later under what conditions that is true. So, next, in order to find out the velocity of discharge, I have to apply the Bernoulli equation. Okay. Between this point here, okay, between this point here and the fluid that is just about leaving the outlet over here, okay, and the fluid that is just about leaving the outlet over here. Okay. So, I will apply it between this point A and this point B. Okay. I know that between these 2 points, okay, P, okay, plus half rho V s square plus rho G h. Okay. I will call h as the height above the bottom surface, I am sorry, height above the outlet. Okay. This h, the height of the surface above the outlet, is actually a function of time. Okay. This height of the outlet of the surface above the outlet is a function of time. Okay. This has to be equal to the pressure plus half rho times the velocity at the outlet square. Okay. At the outlet, the height of the fluid is equal to 0 above this reference level. Okay. So, I can take any reference level and calculate the height with respect to that. Okay. I could have done it with respect to the bottom of the tank, but I have taken the reference level as the height of the outlet. Okay. What is these pressures on the left and the right side? Okay. Obviously, on the left side, the pressure at the top is the atmospheric pressure. Okay. On the left side, the pressure at the top is the atmospheric pressure. On the right side, the tank is discharging into atmosphere. Okay. So, of course, within the tank, the pressure will be equal to the hydrostatic pressure head, the pressure due to the hydrostatic pressure head. But when it just discharges, it is just discharging into atmosphere, and therefore, the pressure at the bottom will also be atmospheric pressure. Just after the fluid is discharged and it has a velocity v 0, the pressure is going to be equal to the atmospheric pressure here as well. Okay. So, therefore, this atmospheric pressure cancels out on both sides. Okay. And I get an equation for H. I get rho g H is equal to half rho into v 0 square minus the surface velocity square. Okay. And I can use this relationship between the surface velocity and the velocity and the outlet velocity that came from volumetric balance conditions. Okay. So, this is going to be equal to half rho v 0 square into 1 minus V s is A 0 by A t the whole square. Okay. That is rho g h. Okay. And from that I can get the value of V 0. Okay, is going to be equal to 2 g h by 1 minus A 0 by A t. The whole square. Okay, this whole to the half power. Okay. So, that is the velocity of the outlet. Okay. The surface velocity is equal to the velocity of the outlet, okay, times A 0 by A t. Okay. And so, I multiply this by A 0 by A t, that is equal to multiplying the denominator by A t by A 0. Okay. Note that there is an exponent of half over here. Okay. So, within the brackets I will multiply it by A t by A 0 the whole square. Okay. And this will turn out to be equal to 2 g h by A t by A 0 the whole square minus 1 whole power half. Okay. The surface velocity, okay, the surface velocity is also the rate at which the height is decreasing. Okay. The surface velocity is the rate of decrease of the height with respect to time. Okay. So, this is equal to minus dh by dt. Okay. That is equal to minus dh by dt, okay, the rate of decrease of height with respect to time, because the surface velocity I have assumed is positive downwards. Okay. Therefore, dh by dt is equal to minus 2 g by A t by A 0 the whole square minus 1 into h power half. or I can take multiply by dt and divide by h power half, and I will get dh by h power half is equal to minus 2g, this will be a half here. Okay, times dt. Integrate both sides, okay, integrate both sides, okay, with the initial condition. Okay. So, if you integrate both sides, I will get integral of h power half is 2 h power half, okay, plus a constant of integration, okay, is equal to minus 2 into t. And that constant is determined from the condition that at t is equal to 0, h is equal to the initial height. Okay. H is equal to the initial height. Okay. So, therefore, if I substitute this in, I will get 2, okay, substitute in and multiply by minus 1. Okay. Okay. So, this will give me a constant c is equal to minus 2 h naught per half. Okay. So, substitute this in and multiply by minus 1, and I will get 2 into h naught per half minus h per half is equal to 2g by whole square minus 1 per half into t. Okay. What is the total time for discharge? The total time for discharge is the time at which h is equal to 0. Okay. So, therefore, the discharge time is going to be equal to, okay, the time at which the height above the outlet is 0, that is the total time for discharge, okay, is going to be equal to at by a naught the whole square minus 1. Okay. Minus 1 divided by g, okay, and I have a factor of h here. Okay. I just did some set h is equal to 0, t is equal to td, and did some algebraic rearrangements, and this is what I get for the total time for discharge. Okay. I am sorry, this should be h naught here. Okay. I have set h is equal to 0. Okay. The final height is 0, initial height is h naught. Okay. So, this is the total time for discharge. Okay. I can substitute the values here. I have 2 into at, tank diameter is 2 meters square. Okay. The tank surface area of the tank is equal to 2 meters square. The diameter of the outlet is 2 centimeters square. Okay. So, I have to divide this by 2. Okay. Okay. So, let me just calculate this. Okay. At is equal to 2 meters square, A0 is equal to pi d square by 4 is equal to pi into 0.02 meters the whole square by 4. Okay, the whole thing minus 1, okay, into 1.5 meters, okay, divided by 10 meters square per second, meters per second square, I am sorry. The whole thing to the half power. Okay. and you can simplify this to get approximately 3487 seconds, which is a little less than an hour. That is the total time for discharge in this tank. Okay. And in this we have used the Bernoulli equation in order to find out the velocity at the outlet. Okay. We have used the Bernoulli equation in order to find out the velocity at the outlet. I said that we wanted to find out the length to which, the maximum length to which the water flows. That we will continue in the next lecture. So, this potential flow, discussion of potential flow, I will continue in the next lecture. I will see you then.